Please welcome on stage Flavio Farroni, co-founder and CEO at MegaRide, Gabriele Fichera, co-founder at BE, CAE and Test, and Diego Minen, CTO at MegaRide. Their presentation illustrates an R&D project developed in collaboration between MegaRide, MegaRide, BE, CAE and Test, and Almatech. The project involved defining a complete methodology for parameterizing the vehicle, characterizing the multi-physics of the tires on any surface, capturing the environment and road texture, and then digitizing them. The floor is yours.
Thank you very much, and thank you all of you for coming to this conference. The presentation that I just give the introduction to is a joint work between several different companies and expertise. Our aim is to clearly do zero prototyping. The team is a nice objective to reach, but to reach that level of accuracy also for us doing developing simulation and driving simulator, we need to know a little bit more and in several aspects what in the real world happens. So let's say we always have been promoting bridging the gap, but everybody thought we are bridging the gap from the software to the real. Now sometimes we also have to go from the real to the software. So I try to give you some idea. Yeah, zero prototypes. Digital twins, sure. We want to go to that level. We can do digital twins of several different components. The vehicle, the tires, the road, and the simulator. All these together could replace basically the real experience. And we started this let's say, joint work more than 1 year ago with putting together all the elements that we make us confident that the digital twin, not much with a specific vehicle, but as a process, could hold to continue the discussion and rely more and more on this duplication. So we are okay with the vehicle model, with the tire model. The road model has always been something that for us basically just inherited from geometrical measurement. But in reality, what we need to be sure of is that the road model and the tire model and the vehicle model are compatible to each other. So which type of work has to be done, for example, in combination with the road and the tire model and the vehicle model to have a reliable result. You will see later. We want to have the full experience on the driving simulator. So we develop a really detailed model of the vehicle. Maybe we go to a simplified model or use the detailed model depending on the application. We use the functional modeling, not only the let's say the independent component specific modeling, but the integration of the modeling is certainly a very important part to consider. And you will learn later what are the detailed activities that need to be done to have this responding to requirement. Obviously, for the functional road model, there is some activity that one has to be done, also measuring and knowing what is required to be captured to provide in the simulator the important feedback for the driver. Then we can probably digitize everything, but the only thing we cannot completely digitize is the human driver. So after we do a really good job, how do we make sure that all this can be perceived by the real driver? Still, we have a real human on board the simulator in the right way. So we have several different subsystems that feed the driver with feedback, haptic, acoustic, vestibular, visual, somatosensorial. And you see in this slide how different delays with different delays they are presented to the driver. And this could come to a critical perception. And I just show you this example. We are in the same time of all the digitalization we do, all the continuous progress in the accuracy of the model, we also study the driver reaction. And in this simple case, we illustrate how, for example, there is a sensory conflict in a simulator when during a braking action, the human expects to receive a certain acceleration, so he pulls the muscle of the neck back, resulting into the head without any consciousness, being tilted downward, while the gaze goes down to keep the horizon fixed. And this is probably creating too much of a rotation, unstable rotation of the head. This is, of course, one has to realize what could be especially in beginner driver and simulator, could be his limit. And one idea that we want to apply and see if it could work is to apply biofeedback on the simulator, like skiers are taught by coach when they see again themselves, for example, during an action. So it is possible to correct a little bit beyond what normally could be thought. With this, I hand over the presentation to Flavio, and enjoy.
Thank you, Diego, for this nice introduction on the perspectives of driving simulation market. So how to move from perspectives to make them happen? We tried with an exercise. We choose a completely unknown track, which is in the south of Italy. We call that seaside racing because the track is quite close to Sorrento, Capri, Amalfi, with group of friends, group of companies, aiming to share knowledge, sharing ideas, share the results of this data. So a potentially unknown track, potentially unknown vehicle, potentially unknown tires, trying to digitalize all of them with the process. So the main idea is starting from multi-physics of the tire with a certain tire that we have on the ground of which we don't know anything at the beginning. Then the part regarding the activity we usually do on vehicles regarding the parameterization inside, for example, car real time. Then there's the road with the devices which allowed us to know something more about that road and virtualizing it and bringing it inside, first of all, the offline simulation channel, and after that on the driving in the loop application. So the targets of the project were optimizing the road texture, geometrical resolution, related to tire modeling and contact multiphysics. Then we wanted to deepen knowledge on tire ride and wear effects on the driving perception. We want to correlate among road geometrical, frictional, and acoustic features of the road patches, and implementing all of that inside the driving simulator for a multisensorial experience. So the first step has concerned our activity were the road and the external environment. So with the proper instrumented vehicle, we had a laser scan integrated photogrammetry and 3 cameras and 2 lasers with a millimeter resolution. We scanned all the road of this track, which is in Circuito del Sele. And the main idea was to clean and filter in the road point cloud in order to generate a grid mesh from 0. And after that, creating a correlation between the measured roughness and the algorithm of the parameters. That was the first step. The second step is assigning to each single point of the grid mesh some specific functional correlation. It means geometrical, frictional, and acoustic features to each different patch of the road, which has been scanned also with a very high definition rugosimeter, which is the AMES 94000 HD. Next step, we moved to tires. We selected the tire, it was a Toyo tire, and we moved, first of all, with several different methodologies to get the tire data from several different procedures. The first one was with our trick tool, which takes the data from the vehicle and allows us to characterize the tires. We also worked with Kelspan and with their bench, and we also mounted a wheel hub by Kistler on the wheel. So we had 3 different ways to understand how the tires behaved. After the kinematics and dynamics, we worked on temperature and energy, so we characterized the thermal conductivity, the specific heat, and the footprints with completely non-destructive methodology of the tires we choose, and we put them inside our thermal model. And after that, once we have the energies and once we have the temperature, we have also the roughness of the road, and we have the viscoelasticity of the tires by means of an innovative device called Vesevo that is in our booth in the next room. We had all the ingredients of the recipe that allows us to talk about wear and degradation. Wear is a very complex phenomenon which talks about many languages which come from so many different phenomena. So after that, we parameterized all our models, feeding a specific identification platform, which is called RideLab, which takes into account all the multiphysical phenomena, so the kinematics and dynamics, the temperature and the energies, and the wear and degradation, putting the right parameters inside the physical models which constitute the right suit tire model. We have an advanced Pacheca model which feels temperature, road roughness, and viscoelasticity. We have a 3D ride multi-contact model that after Gabriele will show us. We have a wheel speed module because, as you know, sometimes MF has some issues with low speeds. We have a thermal module and the wear and degradation module. What we did in terms of operative activity, we understood how we were estimating the forces with our methodologies. So here we can see that with trick methodology, so from the vehicle data to the road, we are able to estimate the forces with very high according with the wheel hub, instrumented wheel hub that we had. After that, of course, we identified our baseline magic formulation. Second step was identifying the thermal model. So we calibrated and we validated the thermal model, taking into account of the measurement that came from the external thread and the inner liner sensors. And once we have properly identified and calibrated the model, we have all the information about the temperature layers which are inside the thread block. Having this kind of information, it's possible to understand how the friction level is changing with respect to the temperature, to identify this kind of trend, putting them inside the advanced Pacheca formulation, taking also into account about the variation in terms of cornering stiffness, braking stiffness, and of course, inflation pressure sensitivity. All these things go inside our advanced formulation, which is called MegaRide, which allows us to put all these things inside the simulations. We also validated these things thanks to some Kelspan data. And what we can observe inside a typical test is that if we identify a Pacheca at the optimal friction level of the tire, we will be able to fit only the results of the Pacheca when it reaches its maximum. But when the thermal level at which the tire is working is too high or too low inside the red and black squares, we see that the normal Pacheca is no more able to fit the friction level and the force level that can be fitted only taking into account of the thermal effects inside the Pacheca model. Finally, once we had all these things, we put them inside our physical wear model. So we were able also to validate the wear on track because we had the acquisition at the beginning and at the end of each run. And so in this way, we have the acquisition in terms of energies, in terms of temperature, in terms of road roughness, in terms of viscoelasticity variations of the compound of the tire, and we're able to know time by time which is the evolution of the tread thickness level of each tire taking part in this activity. I'm leaving the stage to Gabriele for the next slides.
Thank you, Flavio. Good afternoon. Oh, of course, is the last step, but is not last in the order of things that have been done, is the creation of an appropriate vehicle model. Of course, this is a standard procedure, starting from a detailed multi-body model with many degrees of freedom, and even including the powertrain mount system into a car real-time model that can fit and can work in our driving simulator. Of course, there are initial steps that is an offline validation using the offline tools. And of course, we had the possibility not only to make a correlation and validation based on, I don't know what happened, but okay, once again. Based not only on a standard signal like yaw rate and lateral acceleration, but also on forces, lateral, vertical, longitudinal forces obtained from the dyno hub that were installed. Then we moved in offline to a max performance simulation environment, trying to catch the differences coming from different levels of road discretization and road roughness. And of course, having also the possibility to compare even the loads, the calculated loads and the measured loads along the whole track. After this phase of correlation and validation offline, we needed to understand if the feeling of the driver is Claudio Anicello, the driver who is currently running in the demo section at DIM 400, and to receive his impressions comparing the real driving with the driving at the simulator, but not only in a single scenario, but with different simulators, 150, 400, and even the compact, moving from standard operation, which are considered like a sort of chassis tuning towards, we said, zero prototyping, but also to understand the feeling when you change the road surface, when you change when the temperature of tire changes, so the heating of the tire and even the wear effects on it based on the model delivered. And not only this part, but also trying to understand what is the best solutions in terms of road roughness. Here is a representation at the end of the main straight line of the Sele track, when Almatec tried different kinds of way to obtain an efficient point cloud representation, a grid mesh representation of the road. And we had an additional possibility, the possibility that during the old tests, we fitted the car with more than 20 accelerometers channel to measure both hub accelerations, seat rail accelerations, and many other points which were of interest. And so we had also the possibility, in this case, for example, we have a power spectral density calculated using car real-time output, which is the blue one compared with the experiment, the blue one is the measured power spectral density. We had the possibility to compare this PSD against different calculation obtained from car real-time with different condition of roughness levels using the 3D ride model of MegaRide. And finally, we had also the opportunity not only to check the accelerations, but also to make some comparison in terms of power spectral density of forces Here is, for example, in the vertical direction to be aligned to the previous slide, but it's a different point. Let me say the previous one was on the front, this one is on the rear, just to represent the different measurements that we have done and compared with numeric results. And in all this scenario, which tends to zero prototypes, of course, we had the possibility to have the feedback from the driver and to understand how the driver was able to catch, for example, the change in the tire temperature during different laps at the simulator, to change the to feel the change of the car while changing the wear of the tire, or, for example, how the road perception affects his feeling of the car, and how all these parameters can have an effect on the global chassis tuning of the car, because that is to say, there is not a single optimum in terms of chassis, but we need to consider different conditions. And finally, where next? Where next that we were really happy of what we happened by this fantastic opportunity that we obtained on the last year. So we decided to go to a second edition, which was held on the 5th of May. I do hope we will have in the future the opportunity to tell you what we have done. But of course, as you have seen in the first video, we decided to move to deformable soil. As you see, very different kind of vehicles, a rally car. We decided to move also to objectivizing the steering feel, and also to obtain some interesting information by comparing comments from professional drivers and rookie drivers that were ran with the car in that session. But the most important thing, as you can see here on the right side, is that this was for us a great opportunity for sharing ideas and to merge competencies from industrial companies, from the market together with university, which is an additional important value to tend to a zero prototype scenario in a very short time. And that's all. Thank you very much.